All right, so now we are starting on Unit 2. Lots and lots of stuff to be covered in here, logarithms and exponentials, and the first part we're going to get to is going to be arithmetic and geometric sequences. Okay, so a sequence is basically just a function. I can get my pen to stop being silly again. All right, so a sequence is a function from the whole numbers to the real numbers. So that basically means that your inputs, right? So your inputs are the whole numbers starting at 0, and your outputs are any real numbers. Okay, so fractions, decimals, all that kind of stuff. Okay, so we're only able to substitute in whole numbers. That is the rule for sequences. But your output could be anything. That basically the only difference is, as far as it being a function, is that you can't connect the dots, right? It's going to be a set of ordered pairs, but it doesn't actually form a line, even though we consider arithmetic to be linear and geometric to be exponential. That's the form that it takes, but you're never actually allowed to connect the dots. Okay, so this one is a basic arithmetic sequence, and the way it's read, because that is a subscript rather than a superscript, which is like an exponent. So this is a subscript, and it is read as a sub n. So basically a subscript n, and it tells you they're talking about the general form, right? And then it's 4 times n minus 3. They want you to find a sub 1 and a sub 7. That basically means they want you to find the first term and the 7th term. Now I need you to notice something. When we talked about the input, we said the whole numbers. The whole numbers start with 0. Okay, so sequences, arithmetic and geometric sequences always start with the 0th term, so a sub 0. All right, so but when you have the sequence already written, it's basically just plug and chug. You're going to substitute it in and simplify and see what you get. So for a sub 1, that would be 4 times 1 minus 3. It's a lot like function notation, right? When we do f of x and we substitute something in for x, it's the same thing. This literally means substitute 1 in for the n in the problem. So a sub 1 is going to equal 4 minus 3, which is 1. Okay, a sub 7 is 4 times 7 minus 3. In that case, 28 minus 3 is going to equal 25. Okay, so stuff that you've technically been doing since Algebra 1, right? And probably, I don't think we got into sequences much when we did Algebra 2, but we did do the exponential and the logs, which is something else we're doing in this unit. Okay, so the next of it is just how we actually write the formulas. Okay, so big thing about the way arithmetic sequences are defined is that their successive terms have a common difference or a common rate of change, right? Common rate of change should instantly tell you that it follows a linear pattern because you're going to get the same slope or the same rate of change between every 2 outputs, right, in the sequence. Okay, so you can write it as a sub n equals a sub 0. Now we already said a sub 0 is the first term, or sorry, the initial value, sort of like your y-intercept in a linear problem. So your 0th term. Okay, d is your common difference. Okay, so that is for the first way of writing it. The second way of writing it, a sub n equals a sub k plus d, that common difference, times n minus k. So both of these are acceptable as far as how to write them. It's just that a sub k is basically the kth term. Okay, so this is like the form that you use when you don't have that initial value, right? You don't have the y-intercept, and you would have to work backwards to solve for it, which again, something that you did in Algebra 1, if they gave you a point on the line, or 2 points on the line, and then you had to go and find the equation for it, you would find the slope, which would be your common difference, and then you would go back and figure out what your initial value or your y-intercept was. It's not really any different. And interestingly enough, this is basically the equivalent of point slope form from linear equations. Okay, and it's basically set up the same way. You don't necessarily have to remember like the variables, the k and all that other stuff. But if you treat it like it is slope or not slope, point slope form, where you have like the m for the slope times x, or sorry, x minus x1, and then this would be y, and then this technically would be y1, right? Some random point. So basically equals y1 plus m times x minus x1. It's just that they've moved the y1 value over, but this is technically how you write a linear equation if you're given a point, a general point, and the slope, so that you can substitute back in and figure out what the y-intercept is. Okay, so it does work very, very close to the same way. Okay, so as an example that you would see as a graph, okay, so we've got a sub n equals 3 times n plus 1. Could also be written as a sub n equals 1 plus 3n. You know, initial value normally comes first. Okay, so there's your initial value on the 0. And then it has a slope or a rate of change of 3. So that means that's at 4. Number 2 would be at 7, and then we would keep going, and the next one would be at 10. But we're not going to connect the dots because you're not allowed to substitute, right? The inputs are not allowed to be all those fractions and decimals that we want. They're literally just going to be whole numbers. Okay, so let's do a couple of practices ones just to see if we can identify an arithmetic sequence. So if it's arithmetic, that means it is going up by the same amount every single time, right? And technically you should be able to recognize that this is definitely not linear. So you could stop and just say, no, it's not linear because n is squared and that's a quadratic. You could also make an input-output table, right? To prove that your outputs, when we did like the differences between them, are not going to be the same. So if I substitute in 0, I get -3. If I substitute in 1, I get -2. If I substitute in 2, I get 1. If I substitute in 3, 9 minus 3 would be 6. And you could actually prove it, you know, by showing those common differences. Now, we talked a little bit about this before, about when you were looking for not just the rate of change, but when you were looking for concavity, about having to subtract them backwards. You do. In order to actually effectively figure out what your common difference is, you got to go backwards when you subtract. So -2 minus -3 would be 1. 1 minus -2 would be 3. 6 minus 1 would be 5. And we can tell, you know, obviously the first differences are not the same. They're not constant. So this is definitely not linear. Okay, same thing. We know for a fact that this is a linear function if you just look at it as far as the way it's written. We also know that the common difference would be considered the slope, and that would be -2. So again, we could make a table. And again, it's just looking at the whole numbers, right, as far as what we're substituting in. So we substitute in 0, then we get out 6. If we substitute in 1, we get 4. If we substitute in 2, we get out 2. If we substitute in 3, then we get out 0. And we can see, right, that it's going 4 minus 6 is -2, 2 minus 4 is -2, 0 minus 2 is -2. We can see that it is going down by 2 every single time, and being that it's already written in that form, right, then we know we're good to go. That it is an arithmetic and that the common difference is -2. Okay, so this one does not have a common difference, meaning that the first differences are not the same. Okay, so same thing, that we have to subtract it backwards, like I said before. Okay, so -2 minus -7 would be 5. 3 minus -2 would be 5. 8 minus 3 would be 5. 13 minus 8 would be 5. So yes, it's arithmetic, and your common difference is +5. You're going up by 5 every time. Again, that's why we have to start at the second term and subtract the first, and basically going backwards that way. All right, so last one, -2 minus 1 is -3. 3 minus -2 would be 5. -4 minus 3 would be -7, and 5 minus -4 would be 9. No common difference. Okay, so that's a basic as far as if you're given a function, you're given a set of values, just the outputs. You could also be given a table of values with an X and a Y, or an input and an output, however they write it. And you're still going to do that same common difference that we talked about before if you're trying to prove that something is arithmetic, because they are linear. All right, so let's try slightly harder ones that we can actually work with. Okay, so here's the thing. So if I give you a common difference and a term, okay, this is where you're going to use that point slope form, right, of the function, because they've given you basically a general term instead of giving you the first term. So let's write that out just so you can see how it works. Okay, so a sub n equals a sub k plus d times n minus k. And again, it doesn't really matter if you remember the variables. I know a lot of people will put a sub 0 in that, and it's technically not right because we're not looking at the 0th term. We're looking at whatever term we've been given, right? Okay, so a sub k is whatever term we were given. In this case, a sub 3 is 8. So a sub k is 8 plus my common difference of negative 3. And then the n, or the k rather, is what I substitute for the here. So if we say a sub k, right, and k goes together, well, a sub 3 equals 8. Or rather, 8 equals a sub 3. So anyway, so n minus 3 is basically what you do to substitute it in. Okay, it's the third term, and it happens to be 8. So simplify it out by actually, distributing out. So 8 plus negative 3n or minus 3n, it doesn't matter, plus 9, combine like terms. Your general form is going to be 17 minus 3n. Now, if you don't like using this one, it is okay. You can use the other. It's sort of like substituting in your slope and your point into slope-intercept form. It's very, very similar. Equals a sub 0 plus d times n. You can literally substitute in this, a sub 0, and work backwards to solve for your 0 term, and then just write the form. It actually works very similar. The output, a of n, is 8. We're looking for the 0 term. We have no clue what it is. My common difference is negative 3, and I'm looking at the third term. It works the same way, right? You would then add 9 to both sides to solve for your initial value. Add 9 to both sides, you're still going to get 17. It's just then you need to write the actual form, 17 minus 3n. Either way actually works. Okay, whichever one you are more comfortable with. When we get to rational, the exponential ones, the geometrics, we're going to have to use this form. It's the only way to actually work backwards and solve correctly. And I'll show you what happens. Again, it's a little more complicated when you have 2 points, and we're going to discuss that in class. Okay, so anyway, after you write the expression for the initial or for the main sequence, they then want you to use the expression to find a sub 12. Again, that's just plug and chug. A sub 12 equals 17 minus 3 times 12, and 17 minus 36 should be negative 19. Okay, so here's what I'm going to show you what I'm talking about as far as substituting in. Okay, when you're given 2 different values, okay? So what's going to happen is that you're going to end up, if you substitute into this twice, like once for each term, it's going to give you, obviously, 2 different values, right? Either one of them, like you don't have the d, so you would have basically 2 different equations. Let me just show you what I'm talking about before you get confused. Okay, so we're basically just going to substitute into this or the other value twice, okay? So a sub n, that would be the output, that would be 7 equals a sub 0 plus d times 2, right? That's the second term, okay? And then the other equation, same equation, right, would be 9 equals a sub 0 plus d times 6, okay? So just follow along. All right, so what I basically have If I simplify this out, I have 7 equals a sub 0 plus 2d, and 9 equals a sub 0 plus 6d. So think way, way back, right, to solving systems of linear equations. That's what you've just written, is a system of linear equations that you could use to solve for two different variables, right? I can solve for my common difference, or I could solve for my zero term, right? In this case, I'll solve for my zero term. So think way back to solving systems of equations. If you subtract these two, right, the a sub zeros are going to cancel, and you're going to be able to solve for your common difference. So if I subtract them, just set them up one over the other, because they are already lined up, which is kind of nice. Okay, so if I subtract these, 7 minus 9 is negative 2. That cancels. 2d minus 6d equals negative 4d. And then if I divide to solve for my common difference, right, I'm dividing by negative 4. D is equal to a half. So now I have my common difference, and I can go back and do what I did before. This is the first thing that you always have to solve for, is your common difference. It's just the way that's going to work. Okay, so now I can go back, like I said, and do what I did before, using either one of these terms and using either one of these forms, whichever one makes you more comfortable. So I'm going to do both just so we can actually practice it. N equals a sub 0 plus dn. All right, so I'm going to use 2. My second output, 7 equals a sub 0 plus 1/2 times 2. 7 equals a sub 0 plus 1. Subtract 1 from both sides. My initial term is 6. That's doing it in that form. Okay, if I do it in the other one, again, whichever form you are comfortable with. All right, so a sub n equals, again, the variables don't matter if you think about it in terms of the point slope form. We should be good. Plus d times n minus k. And again, that a sub k just basically allows you to plug in whatever value you've been given. Okay, so I'm going to use my second value. So that's 7 plus 1/2 times n minus 2, since I'm looking at my second value. And again, distribute and simplify. 7 and negative 1 as far as like terms is 6 plus 1/2 n. So literally going to get the same thing, whether you solve from this, and then just don't forget to actually write your actual form, or if you substitute it into the point slope form and just simplify it from there. Either way, doesn't matter. Okay, so we have the expression. Again, it's quite a lot of work, yes, but this is how we do this as far as solving. Then substitute in 24, since we want the 24th term. Oh, where did my pen go? Okay, there we go. No, now it's just being weird. Okay, so I want the 24th term, so 6 plus 1/2 times 24. 1/2 of 24 is 12, plus 6 should be 18. Okay, so again, that's just given a couple of values. Okay, so this one is not nearly as bad, only because they give you the zero term, right? So we're just going to write the expression. Since we know if it's on the y-axis, that has to be my initial value, which means I already have a sub 0, right? And then my question is, again, remember we have to subtract backwards. 6 minus 8, since I'm only subtracting the output, the y values, 6 minus 8 equals negative 2, and that is my d value, my common difference. So the formula, again, for this one, very, very easy. Initial term and common difference. And then we're just going to substitute in 17. 8 minus 2 times 17. That's 8 minus 34, which I think is negative 26 off the top of my head. Okay, so let's go ahead and take a look at geometric, which is, again, slightly different and takes a little bit more work as far as to work around it. Okay, and then we will actually finish this in class tomorrow. Okay, so geometric. All right, so geometric, like I said, are exponential, and that means they have what's called a common ratio, or basically proportional change, which means you are multiplying, even if it's by a fraction, you are multiplying to get your successive terms. Okay, remember ratio is just basically a fraction, so there's times you will have, your numbers will be getting smaller because you're actually multiplying by a fraction. Okay, so same deal as far as what the pieces are. The sub-zero is always going to be your initial value. The R in this case is your common ratio, and that's why they give it the R variable. And then your G of K is just your kth term. So again, that's like one of where we can actually substitute in and solve for a initial value if we need to, to actually write the whole formula. Okay, so again, not continuous, so no connecting the dots. So please make sure you're paying attention to that. It is just points. Okay, so if I want to graph this, right, I already know that my initial term is 8, right, because it's written in the first form, not the second form. It doesn't have the n minus k on it. So my initial value is 8, and I am multiplying successive terms by a half. So if I needed, again, to make a chart, 0, if I substitute in 0, anything to the 0 power is 1, so it's just 8 times 1. That's why it's 8. First term, 8 times a half would be 4. Second term, well, 1/2 squared is 1/4, and 8 times a fourth is 2. And again, basically just, dividing by 2 and multiplying by a half is the same thing. So this one should be 1. And then we start getting into where it's going to get smaller and smaller, but never actually reach 0. Okay, so 8, and then 4, and then 2, and then 1. And then, like I said, if I want to keep going, I'm not going to connect the dots, but you can tell just by the shape of it that it's most definitely an exponential. Okay, so same deal. Let's determine if they are geometric. Now again, if you're given a function, it is very, very obvious whether or not it is a geometric. It should look like an exponential function, which means the exponent should be a variable. This one does not have an exponent that's a variable. Again, I can make a table of values just to go with it. Substitute in 0, and I get 0. Substitute in 1, and I get 3. 2 will give me, 4 times 3 is 12. 3 will give me 27. And then I could go back and actually prove it by showing that I am not getting a common ratio. Now, ratio means fraction, means divide, so you need to understand what that means, and we're going backwards. 27 over 12 is 9/4, I think, is what it reduces down to. 12 over 3 would be 4. 3 over 0 doesn't exist. So you can see that you are not getting a common ratio every single time. You're not getting that rate of change. If you want to, treat it like that, you're dividing now instead of, subtracting. But you're not getting that common ratio or common fraction every time. Okay, again, looking at this one, this is most definitely an exponential function. So that means it is geometric. So again, let's just prove it so that we can actually see what's going to happen with our outputs, our ratios. All right, so if I substitute in 0, I get out 2. 0 minus 1 is -1. 2 raised to the -1 is a half. Yeah, so that's 2. All right, first term, that's going to give me just 4. Second term, and again, use a calculator for this if you're getting struggling. Just make sure you put that whole thing as the exponent, like the x minus 1. 2 minus 1 is 1. 2 first power, that should be 8. And that means 3. 3 minus 1 is 2. 2 squared is 4 times 4 should be 16. And as you can see, it's growing by the same amount every time. But again, we can check it. 16 over 8 is 2. 8 over 4 is 2. 4 over 2 is 2. Common ratio, right? You're multiplying by the same amount every single time. So yes, it is, and R is 2. It's written there in the function. Okay, so same here. We are going to divide backwards, like I already said. Okay, so. All right, so 3 divided by 1, 2 divided by 3. I can quit now. because I'm already not getting the same ratio. 6 divided by 2 is 3. 4 divided by 6 is 2/3. I'm going back and forth between two specific ratios. That's not a geometric sequence. That's something that you'll see later in calculus if you end up taking that. So no common ratio. Okay, same goes here. Again, we're just dividing second term by the first. So -8/16 is -1/2. Okay. 4/8 is also -1/2. -2/4 is also -1/2. And then 1/2 is -1/2. So yes. And my common ratio is -1/2. -1/2. Again, given a table of values, given an equation, given a table, or given a graph, it's very much the same thing like finding your common differences before. Again, though, when you see the outputs, and again, hoping, if I look at something like this, or I look at something like this, the output for for B, where it's 2, 4, 8, 16, and it would keep going, I already know looking at it, I'm not adding by the same amount every single time. There is another way that you can do it, as far as if you're looking at your differences, instead of like if you do one difference and it's the same, then it's going to be the arithmetic. If you keep taking the differences and you just keep getting the same pattern over and over again, like if I were to take the differences in these numbers, that would be 2, that would be 4, that would be 8. So notice it follows that same pattern that was already there, 2, 4, 8. If I took the differences again, it would be like 2 and 4. You keep getting a repeating pattern. That's automatically an exponential or a geometric. And that is just the way that works for those differences. Okay, so into a little bit harder. Okay, so again, we have two possibilities on how we're going to do this. I am going to do both, and then we're going to talk about why both answers are correct, just so that you can, deal with it. You already know, hopefully, remember some of your exponent rules. All right, so G of 1 is 12 and R is 2. So let's use the one technically that we're supposed to, right, when you're given a term that is not the first term. So G of K times R raised to the n minus K. And we're just going to substitute in what we have. We have 12 as our output. Our common ratio is 2, and I'm looking at the first term, so n minus 1. Okay? And I am going to simplify that as much as I possibly can so that I can find my first term. Okay, so again, if you remember your exponent rules, okay, what was I allowed to do, like when I saw something and I was allowed to subtract exponents? If you remember, when you're subtracting exponents, you were dividing their bases. So technically this 2, right, this 2 can be written as 2 to the n over 2 to the first, because that's technically what that was, like bases subtracting exponents, right? Okay, so what you have is 12 times 2 to the n over 2, because that's 2 to the first, right? Well, can we reduce the 12 and the 2? Yeah, 12 over 2 is 6. So technically, your first term, right, is 6, and then your common ratio, or your zero term is 6 rather, your common ratio is 2, and it's raised to the n. Now, I could have just as easily, again, substituted into the other form, right? I don't know my zero term, so the G sub 0, and then it's R to the n, right? So I'm going to do the same thing. I plugged in my first term and got 12. I don't know my initial term. I know my rate is 2, and this was supposed to be a 1, right? You basically have 12 equals something, running out of room, something times 2. So wouldn't you automatically go ahead and divide 12 by 2, right? If you're solving for whatever that something is. So it'd still give you that your initial term is 6. So it works either way. With this way, you are going to have to remember your exponent rules because of the subtracting. It's always going to be a subtraction one, by the way. As long as you remember that when you're subtracting, you're dividing, it's actually pretty easy to simplify. Just saying. Anyway, we got our form, and now we are going to find G of 4. So 6 times 2 to the 4th power. Okay, so 2 to the 4th power is 2, 4, 8, 16. And 16 times 6 is 96. Now, theoretically, you could have also left it like this. And if you substituted in 4, you would have done 4 minus 3, right? 4 minus 3, or 4 minus 1 rather, is 3. 2 to the 3rd is 8, and 12 times 8 is also 96. So technically, both of these would be correct. It's just that this one is the more simplified if you're trying to find your first term. All right, so let's try one with a graph. Again, fairly easy because they've already given you your 0 term, or your initial value. And we need to divide, right, to figure out what our common ratio is. So it's 4 divided by 8, which is a half. That's your R. So again, plug and chug. G of n, initial value is 8. Common ratio is a half, raised to the n power. If I want the 10th term, just substitute it in. 1/2 to the 10th power. That's 1,024. Lord have mercy, 8 on top. Use a calculator. I know it's going to reduce down to 1 over 128. So 8 over 1024 is what it should end up being before it reduces. Okay, so we are done for now. We are going to go over the rest of the geometric tomorrow in class so that I can show you specifically how we work with 2 geometric points and actually writing a sequence from there, or writing a formula for a sequence from there. All right, see you next time.